Hello everyone, welcome back, and today we will go over the newly released 2021 AP Chemistry FRQ number 1. So the first question, methanoic acid HCOOH ionizes according to the equation above, and we want to write the expression for the equilibrium constant Ka for this reaction. So what we want, let me change the color here, is Ka. And we know Ka is products over reactants, and we exclude pure solids and liquids. So the Ka expression is the concentration of hydronium plus HCOO minus all over methanoic acid HCOOH. We exclude water because it's a pure liquid. So that's part A. And part B, you want to calculate the pH of a 0.25 molar solution of methanoic acid. So now, we want to set up a rice table. Oh, that was a really terrible R. Whatever. So the reaction we can just copy from what they gave us. I'm not going to write water because it's not part of the equilibrium. No, it's H plus. So the initial concentration is 0.25, and before any reaction happens, there are no H plus or HCOO minus. Then the change in concentration is unknown. We actually subtract X from this, and we add X. So now the equilibrium concentration would be 0.25 plus, I keep writing plus, excuse me, minus X, X, and X. So now we have the equilibrium constant Ka is equal to X squared over 0.25 minus X. We want to solve this for X, which gives us the concentration of hydronium, which is needed for the calculation of pH. So now we'll move this here. So we have 1.8 times 10 to negative 4 is equal to X squared over 0.25. And I'm going to drop the minus X because the percent association of this reaction is less than 5%. So the minus X is negligible. So now plug this into your calculator. Times negative 4.725. Take the square root. So now we have X, which is equal to the concentration of hydronium, or H plus, equals, well, I'll say approximates to 0.0067. And then now you take the negative log of this thing, and now the pH should be 2.17. So that will be part B. Now part C, we want to draw the Lewis electron dot diagram for HCOOH. So I'm going to write this next to it. OOH. So I'm not going to write the dots yet because it's a bit messy. So first, we know hydrogen only makes one bond, right? So you can just draw a line between the two hydrogens because they only make one bond. Oxygen makes two bonds. So this oxygen right here, since it's already making one bond with one hydrogen, it can only make one extra bond with a carbon. Now this oxygen here is not making any bonds, and it can make two bonds. And carbon needs 4 bonds. So therefore this has to be a double bond. So this is the skeleton for what we need to fill out here. But now we need to draw dots, so we can base off what we have here. So one pair of electrons for one single bond, and this one as well. This one as well. So these are our single bonds. Now for the double bonds, it will be 4 electrons, or 2 pairs of electrons. So there are our bonding valence electrons, but the question is also asking for the non-bonding valence electrons. So now oxygen will have a total of 8. So now there should be more here and more here. So now if you count the electrons that each atom possesses, they should all sum to 8 with the exception of hydrogen, which is 2. So that is your final answer for part C. Now for part 3, in aqueous solution, the compound H2 and NH2 reacts according to the equation above. A 50 milliliter sample of 0.25 molar H2 and NH2 is combined with 50 milliliter sample of 0.25 molar HCOOH. We want the balanced net ionic equation for the reaction that occurs when this is combined, when the two chemicals are combined. So when we look at this, they are all molecular compounds. So there are no spectator ions. So you don't cross anything out when you're writing the equation here. Alright, so the net ionic plus the acid, also aqueous, reversibly yields the conjugate base, the conjugate acid with a plus formal charge, and now the conjugate base of methanoic acid. And of course, write your phases. So that is the complete balanced net ionic equation for the reaction. Remember, no spectator ions because there are no, alkali or alkaline earth metals here, or just any metal in general that can act as a spectator ion. So now the next question, the follow-up, is asking, is the resulting solution acidic, basic, or neutral? So now we want to look at the Ka versus the Kb, right? So now they gave us the Ka back here, which is 1.8 times 10 to the negative 4. I'm going to write that down. 1.8 times 10 to the negative 4. And then Kb, it's given here, is 1.3 times 10 to the negative 6. So now, since Ka is greater than Kb, the solution should be acidic. It makes sense because the dissociation constant Ka is larger than Kb, so there should be more hydronium than hydroxide in solution. So that takes care of part D. Now part E. When a catalyst is added to a solution of methanoic acid, the reaction represented by the following equation occurs. So you have HCOOH yields H2 plus CO2. Is the reaction a redox reaction? So redox reactions involve transfers of electrons, so there has to be some kind of change in oxidation state. So now we can label all of these elements with their oxidation states. So we know oxygen here, this might look like a peroxide, but according to our Lewis electron dot diagram up here, this is not a peroxide. So therefore, the oxygens are -2 each. So -2, -2. Now hydrogens, when covalently bonded to nonmetals, are +1. And to balance out this charge, the carbon has to be a +2. So hydrogen is +1, carbon is +2, and oxygen is -2. Now in the products, the hydrogen, since it's a neutral species here, the oxidation state is 0. Now the oxygens are still -2 each. So now that makes this carbon +4. Now as you can see, the oxidation states of hydrogen and carbon have changed. So this is definitely a redox reaction. So you would answer yes. And then you will cite that the ox state for H changed from +1 to 0, and ox state for carbon changed from +2 to +4. So there's a movement of electrons, so that's redox. So now part F. The reaction occurs in a rigid 4.3 liter vessel at 25 degrees Celsius, and the total pressure is monitored as shown in the graph above. The vessel originally did not contain any gas. Calculate the number of moles of carbon dioxide produced in the reaction, and assume that the amount of carbon dioxide dissolved in solution is negligible. Okay, so now you're given a question. It involves gas. You're given temperature, you're given volume, and you want to find moles. So this should ring a bell, the ideal gas law. PV is equal to nRT. Right? So now let's work with this. So you're given the pressure. The pressure at the end of the reaction, if you look at the graph, is 24 atmospheres. I'm not going to write units. And the volume is 4.3 liters. And you're trying to determine the number of moles. R is the ideal gas constant, 0.826. And the temperature, they gave the temperature 25 degrees Celsius, and you want it in Kelvin. So you add 273 to get 298 Kelvin. Now you solve for N. So plug all of this into your calculator. 24 times 4.3 divided by 0.08206 times 298. So now the number of moles is 4.22 moles of gas. So now you want to find the moles of carbon dioxide, but you only solved for the moles of gas. But if you look up at the equation above, I'm going to clear all of the annotations for part E to make it cleaner and more visible. Okay, so if you take a look at this equation, these are both gases, so gas evolution, it's not reversible, as shown by the single-headed arrow. So therefore, this reaction goes to completion. So all of this methanoic acid is gone. You only have hydrogen gas and carbon dioxide gas. Now, the hydrogen gas and carbon dioxide gas are produced in a 1-to-1 molar ratio. You have 4.22 over 2, which is 2.11. So therefore, there's 2.11 moles of CO2 produced, and that would be your final answer. Now, the last part, part G. After the reaction has proceeded for several minutes, does the amount of catalyst increase, decrease, or remain the same? Justify your answer. So you should know that catalysts are not consumed in the reaction, so it should remain the same. And then you would say that catalysts are not consumed. So now, to demonstrate this, I'll talk about a side reaction. So for example, you want to talk about the depletion of ozone in the upper atmosphere. So you have an overall reaction that goes something like this. And then you have two steps to the reaction. So step 1, you have O3 plus Cl, and step 2, So the chlorine here is a catalyst. You see, you add it to the reaction, it gets consumed, but then in the second step, you reform it, so the amount of catalyst does not change. So therefore, this question, the answer to this question is it remains the same and catalysts are not consumed. So this wraps up question 1 of the 2021 AP Chemistry Free Response question 1. Thank you for watching.